over a temperature difference which is not too large, then its volume remains constant, and the heat transfer rate during that process is simply equal to mc into delta T, and for a solid specific heat at constant volume and constant pressure will be same. So it's simply mcp into delta T, and the entropy change S2 minus S1 is nothing but mc ln T2 by T1. Okay. Now let us look at another simple process that's known as constant pressure or isobaric process. So the iso here stands for a constant. That means whenever we say iso something, that means some property is remaining constant. So in a isobaric process, the pressure remains constant. And here let us take the example of again a non-flow process. We are heating or cooling a gas which is contained in a piston cylinder assembly. And let us say that the piston is not spring loaded or anything, that means it is acting against a constant external force. If that is the case, the pressure remains constant, that means the pressure exerted by the piston remains constant. And if you assume that the piston is frictionless, that means the movement takes place without any friction, then we can have an ideal isobaric process. And for this isobaric process, the equations are like this. For example, this first equation is nothing but first law of thermodynamics for an isobaric process in a non-flow process. Okay, and as you know very well, this is nothing but the statement of first law. Okay, 1q2 is nothing but u2 minus u1 plus 1w2. And how do we find 1w2? 1w2 for a non-flow process is the integral pdv, and if you assume that this process is quasi-static, then you can perform the integration, and since pressure is constant, this is simply equal to p into v2 minus v1, where V2 is the final pressure and V1 is the initial pressure. So work done during a constant flow process is nothing but P into delta V or P into V2 minus V1. And the heat transfer rate can also be written in terms of enthalpy difference. For example, if you are substituting this here, and if you are using the definition of enthalpy, H is U plus PV, and P is constant here, you can get this equation. Okay, that means you can write 1q2 as m into H2 minus H1, where m is the mass of the system and H2 is the specific enthalpy at the final state, and H1 is the specific enthalpy at the initial state. And H2 minus H1 can be written in terms of specific heat at constant pressure and temperature difference. That means 1q2 is mcp into delta T or mcp into T2 minus T1. And using the second TdS equation, you can obtain this relationship for change in entropy. Okay, if you remember, second TdS equation is given as TdS is dH minus VdP. So VdP is 0 because pressure is remaining constant. So ds is integral dH by T, and if you are performing the integration between state 1 to 2, you get the expression for entropy change during an isobaric process. Okay. So let us look at another process. This is known as a constant temperature or isothermal process. A typical example of this is compression expansion of a gas with heat transfer. That means again we are taking a non-flow process. A gas is undergoing compression or expansion in a piston cylinder assembly, and at the same time the heat transfer is taking place between the system and surroundings. The heat transfer is taking place in such a way that the temperature of the system remains constant. So this is then the process becomes an isothermal non-flow process. And for this process, the governing equations for energy, for work transfer and heat transfer and energy entropy transfer are given here. Okay. For example, this equation is nothing but your first law of thermodynamics for a non-flow process, a general first law of thermodynamics for a non-flow process. And since you have volume change here and pressure also can change, the work done during this process has to be obtained by integrating this process 1 to 2. And so you must know the relationship between P and V in order to perform this integration and in order to find out the work done. Of course, the process has got to be quasi-static, otherwise you cannot, or quasi-equilibrium process, otherwise you cannot perform the integration. And if you assume that this fluid behaves as an ideal gas, then U2 will be same as U1, because for ideal gas, if you remember, the enthalpy and entropy changes are functions of temperature only. So for an isothermal process, temperature remains constant. That means internal energy has to remain constant and enthalpy also has to remain constant, because both are functions of temperature only. If that is the case, and if you are applying this conclusion to the first law of thermodynamics, you will find that U2 is equal to U1. So you end up with this equation. That means heat transfer is equal to work transfer, okay, for this process. And if you are assuming the gas to be ideal, you can replace P using this equation. PV is MRT, replace P by MRT by V and perform the integration, so you get this equation, okay. And you can also write the work transfer rate in terms of the pressures, okay. So this is these equations are for the work transfer and heat transfer of an ideal fluid undergoing an isothermal non-flow process, okay. And how do we find the entropy change? Again, you can use the TdS equation, either the first TdS equation or second TdS equation. Since temperature remains constant, you don't have the du or dh terms, so you just have these terms only. That means the second terms of the TdS equations, and if you perform integration, you get these equations. Of course, you can get some conclusions out of this. For example, look at the work transfer equation. If the system is undergoing expansion, that means P1 is greater than P2, then this will be positive, okay. And if it is expanding, system is doing work, so 1W2 is positive, okay. So that is in accordance with our sign change. And if the system is undergoing compression, P1 will be less than P2, that means this will be negative, and 1W2 will be negative. That means you have to supply work to the system, okay. And same similar conclusions for entropy change can be obtained by looking at this equation. For example, if when it is expanding, that means when it is doing work. When it is doing work and if its temperature has to remain constant, that means there must be some heat transfer from the surroundings, only then the temperature can remain constant, okay. That means heat transfer is positive, okay, because work transfer is positive, heat transfer is positive. When heat transfer is positive, you are adding heat to the system, that means its entropy has to change. So that is the case here, because S2 minus S1 has to be positive because entropy is increasing. This holds good here because P1 is greater than P2, so this is positive, this is also positive, okay. Now let us look at another simple process known as an adiabatic process. Generally, adiabatic process means a process in which there is no heat transfer, either to the system or from the system, okay. That such a process is known as an adiabatic process. You can have an adiabatic non-flow process or an adiabatic flow process. Let me give you an example of an adiabatic non-flow process. The example given here is compression and expansion of a gas under perfectly insulated conditions. So you have, let us say, that a piston cylinder arrangement, a gas is contained within the piston cylinder, and you are compressing or expanding the gas, and at the same time all the walls of the system are perfectly insulated, okay. So such a case is an example of an adiabatic process. All adiabatic processes follow the general equation PV to the power of K is constant capital K, okay. And here P is the absolute pressure and V is the volume, and K is known as coefficient of adiabatic compression or adiabatic expansion, okay. And for such a process, the heat and work transfer rates can be conditions. So you have, let us say, that a piston cylinder arrangement, a gas is contained within the piston cylinder, and you are compressing or expanding the gas, and at the same time all the walls of the system are perfectly insulated, okay. So such a case is an example of an adiabatic process. All adiabatic processes follow the general equation PV to the power of K is constant capital K, okay. And here P is the absolute pressure and V is the volume, and K is known as coefficient of adiabatic compression or adiabatic expansion, okay. And for such a process, the heat and work transfer rates can be obtained again using the first law of thermodynamics processes for a non-flow situation, okay. That is this is a general first law of thermodynamic equation. So 1Q2 is obviously 0, right, because it's an adiabatic process, so no heat is transferred to the system or from the system. So this is the first law of thermodynamics for an adiabatic process, Okay, and since this term is equal to 0, the work transfer rate must be equal to the change in the internal energy. That is what is shown here. And if you are using this equation along with this equation, you get this expression for work transfer rate. Okay, so that means work transfer during an adiabatic expression is given by K divided by K minus 1 into P2 V2 minus P1 V1, which is nothing but U1 minus U2. Okay, so this is a typical work transfer for an adiabatic process. And if the process happens to be reversible, let us say, that then we have reversible adiabatic process. A reversible adiabatic process is also an isentropic process. How do you prove that? That means a reversible adiabatic process is an isentropic process. That means entropy remains constant. It is very easy to prove this. If the process is reversible, we can use the Clausius inequality that heat transfer rate during a reversible process is nothing but integral TdS. Okay, and since 1 Q2 is 0 here because it is adiabatic, integral TdS must be 0. Since T cannot be 0, obviously ds has to be 0. That means S1 is equal to S2. That means a reversible adiabatic process is also an isentropic process. Okay, and if the fluid behaves as an ideal gas, then you have an additional relation. This isentropic coefficient K is nothing but isentropic coefficient which is equal to the ratio of Cp by Cv. Okay, and for compressible fluids you can get an additional relation, this additional relation which relates the temperature with pressure ratios and volume ratios. For example, T2 by T1 is related to the pressure ratio by this relation, and it is related to the volume ratio by this relation. These equations are very, very useful, and we shall see the use of these equations when we perform the actual refrigeration calculations. Okay, now let us look at another process called as a polytropic process. A polytropic process is a general process. A typical example of this process is compression or expansion with heat transfer. That means we have a piston cylinder assembly, and this assembly consists of a fluid, and that fluid is undergoing compression or expansion, and you are not ruling out the possibility of heat transfer. That means during compression and expansion there is some heat transfer between the system and the surroundings, and here the system means the fluid which is undergoing compression or expansion. Such a process is called as a polytropic process, and all the polytropic processes follow a general relation given by PV to the power of n is constant, where P is again absolute pressure, V is the volume, and n is known as polytropic coefficient, and this n can take values anywhere between minus infinity to plus infinity. That means almost all the processes fall under this polytropic process. For example, where for an isobaric process P is constant. So this is the example of an isobaric process. P is constant, that means n has got to be 0. Okay, so when n becomes 0, P becomes constant, so this polytropic process reduces to an isobaric process. Okay, and when n is equal to 1, PV is constant, and this becomes an isothermal process, P is constant. Okay, and for an isentropic process the n simply becomes the polytropic coefficient simply becomes adiabatic coefficient, that means S is constant. Okay, and for an isochoric process volume is constant, that means n is equal to minus, sorry it is not printed here, n is equal to minus infinity. Okay, so depending upon the value of n, the polytropic process encompasses all the processes. Okay, so this is a very general process. Now how do we find the work transfer and heat transfer during a polytropic process? So that is given here. Again I am taking an example of a flow process. Okay, and the work transfer rate here is obtained by integrating integral PdV. Okay, along with the expression PV to the power of n is constant K. Okay, if I am using this these two relations, I can get this equation by integrating PdV. Okay, and this is the general expression for internal energy change. Internal energy change is given by mc into delta T, where phi is the average specific heat at constant volume. Okay, and this is nothing but your a statement of first law of thermodynamics for a non-flow process. What we have done here is 1 Q2 is nothing but U2 minus U1, and this term is nothing but your work transfer rate. Okay, so this is simply your heat transfer in a polytropic process, and the general entropy equation for entropy change in a polytropic process is given by this. This is nothing but the integration of the TdS equation. That means when you perform the integration of the first TdS equation, you get this kind of an expression, and depending upon the relationship between du and T and PdV and T, you can find out what is the entropy change. Okay, for example, if it is let us say an ideal gas, then you can write, and if you are also assuming that Cv is only a function, Cv is constant, then you can write this as Cv dt. Okay, similarly P can be expressed in terms of P by T can be expressed in terms of V. Okay, and you can get expression for S2 minus S1, and this equation is valid for all n except n is equal to 1. So when n is equal to 1, obviously here this becomes you cannot evaluate this. Okay, in such case n is equal to 1, the process becomes isothermal, and as we have seen how to evaluate work transfer for an isothermal process. Okay, and the last process is what is known as a constant enthalpy or isenthalpic process. This is again a very important process as far as refrigeration is concerned, and a typical example of this is the throttling of a fluid. That means a fluid is flowing through a conduit and suddenly it encounters a resistance. Okay, for example, a fluid is flowing through a tube and suddenly a valve is there in the tube and valve is almost closed. So the fluid has to flow through an almost closed valve. That means a large resistance is suddenly imposed on the fluid flow. Okay, obviously what happens, there will be large amount of friction, and because of the friction the pressure drops. That means there will be an expansion. Okay, the pressure drops from the inlet pressure to an exit pressure. Okay, so this is an example of a throttling process. Throttling process also takes place when you are forcing the fluid through a narrow tube, for example a capillary tube in a vapor compression refrigerant system. Okay. For a typical throttling process, if you are assuming a flow process, that means let us say that we are assuming the process to be steady flow. Okay, and if you are also assuming that the kinetic and potential energy changes are negligible during this process. Okay, then this is nothing but for such kind of a process, if you are assuming that the throttling is taking place in a small area, then there is no area available for heat transfer, so Q dot will be 0, and no work done during this process, so W dot is also 0. So Q dot and W dot are 0 for the throttling process in a steady flow. Okay, and if you are applying the steady flow energy equation which I have discussed in the last class, under these assumptions of negligible kinetic and potential energy changes and no heat and work transfers, you get this equation. Okay, that means finally the throttling process is an isenthalpic process. Doing the fundamentals of heat transfer and fluid flow. Okay, thank you.